Hi Math 215 students. In this video we're going to talk about the inverse of a matrix. We'll define it and we'll talk about the 2 by 2 case. Here are outcomes for the video. We'll take a look at this list at the end. Now after the prologue that we've seen, some of these concepts will be not exactly new to you, but we're going to define them formally and talk about some details. So we'll start right away by saying that if A is an n by n matrix, then if B is another n by n matrix and it satisfies these two conditions, A multiplied by B is the identity matrix of the same size, and B multiplied by A is also the identity matrix. If those two are true, then we will say that B is the inverse of the matrix A. Now we'll point out the identity matrix has to have the same size as A and B, just because of matrix multiplication. But let's take a look at an example of a matrix that has an inverse. 1, 2, 3, 5, and the matrix negative 5, 2, 3, negative 1 have the property that if you multiply them in either order, you're going to get out the 2 by 2 identity matrix. Hopefully you can take a few seconds and verify that that's true. But what that means is that negative 5, 2, 3, negative 1 is the inverse of the matrix 1, 2, 3, 5. Now if you kind of switch the roles of A and B, you'll see that actually 1, 2, 3, 5 is the inverse of the matrix negative 5, 2, 3, negative 1. These two matrices are inverses of each other. Now we'll hasten to say right at the outset that not every matrix has an inverse. Having an inverse is a special property that's kind of above and beyond what a normal matrix does. But what we'll do is we'll say that matrices with this property, that they have an inverse, are called invertible. Not every matrix is invertible, but we're going to be talking about the ones that are, and we're going to explain how you can tell whether one is invertible or not. Here are some more examples of invertible matrices. Negative 4, 6, negative 7, 10 has an inverse in the form of 5, negative 3, 7 halves, and negative 2. If you like, pause the video and check the details, but if we multiply those two matrices in either order, we'll get the identity matrix out. And then here are two 3 by 3 matrices. This one would really take a minute or two to verify the details, but if you multiply them in either order, you're going to get the 3 by 3 identity matrix out, and that means that these two matrices are invertible and they are inverses of each other. Now, we need a little bit more vocabulary. We've been talking about invertible matrices. We're going to introduce another term, and so what we'll start off by saying is that invertible matrices, like these ones that we've seen on past slides, these are also called non-singular matrices. And the reason we call them that is because a matrix that does not have an inverse will be called non-invertible, or if we get tired of referring to these as non-matrices, we'll instead call them singular matrices. So singular matrices do not have an inverse, they're not invertible. And here are two examples of singular matrices. There's the 1, 2, 3, 6. This is the matrix we saw in the prologue that just seemed to have weird properties when it came to multiplication. It turns out that it does not have an inverse. We'll explain even more why not in the coming slides. But then take a look at this matrix on the left, the zero matrix. The zero matrix, I claim, does not have an inverse. And if you were to think about why that would be, if there were an inverse B to this matrix, I'd have to be able to multiply B onto the zero matrix and get the identity matrix out. Or I'd have to take the zero matrix and multiply by B afterwards and expect to get the identity out. But that can't happen because the zero matrix times anything is just going to produce a zero matrix. So there's no way we can produce the identity matrix from the zero matrix. So the zero matrix is definitely a singular matrix. It definitely does not have an inverse. We've been talking about the inverse of a matrix. We're going to explain why we say that. It turns out that each invertible matrix has only one inverse. In other words, there is a unique inverse for each invertible matrix. All that says really is that if I know that 1, 2, 3, 5 has negative 5, 2, 3, negative 1 as an inverse, And if I were to try to answer this equation by filling in this matrix, there's only one way to do it. The inverse is the only thing that fits in here, and there is only one inverse. So negative 5, 2, 3, negative 1 would be the only way to fill in these blanks to get the inverse out. Why is this true? I'm telling you there's only one inverse, but why? Well, let's do a little bit of a thought experiment. Let's suppose that A is an n by n invertible matrix, and let's suppose that you know an inverse B for that matrix A. And I also know an inverse C for A, but we don't tell each other the inverse we're thinking of, and for all we know, I might be thinking of a different inverse than you are. Well, with that setup, let's try to simplify the quantity B times A times C. I just suggest that it would be interesting to look at this. Remember, B is the inverse of A that you know, and C is the inverse of A that I know, but we don't tell each other what they are. So we're going to simplify this, but remember that because of the associative property, we can group the multiplications in either way. So I can either multiply A and C first and then multiply B on the left afterwards, or I can multiply B and A first and multiply by C afterwards. So let's start on the left-hand side. Remember that A and C are inverses. C is the inverse that I know for A. So when I multiply those together, A times C becomes the identity, and then multiplying B on afterwards on the left gives us the matrix B. So BAC just simplifies to the matrix B. On the other hand, B was the matrix that you knew to be an inverse for A. So B times A is the identity, and the identity times C is just C. And so this quantity BAC simplifies to just C. Well, what that means then is that B and C are the same thing. They're equal. If there were different inverses for A, it's definitely possible you could think of one and I could think of a different one. But what this expression is telling us is that we are guaranteed to be thinking of the same thing. And the only way that can be true all the time is if there is just one inverse. When you think of the inverse of A and I think of the inverse of A, we have to be thinking of the same thing because there's only one of them. All right, well, that was an interesting, fun thought experiment. This is why we talk about the inverse of a matrix A. And while we do, we'll introduce some notation here. A raised to the superscript of -1. This is how we write the inverse of A. This is in analogy with the reciprocal of a number, 7 raised to the -1. We interpret that to mean 1 over 7. We interpret that to mean the thing that when you multiply it by 7, you get 1 out. Or if you were to think of the exponent rules, -1 plus 1 gives us 7 to the 0. That also equals 1. We don't necessarily talk about reciprocals of matrices, but in our prologue, we kind of asked if there were matrices that acted like reciprocals, and that's where this idea of an inverse came from. So we won't call these reciprocals or write them in fractions with 1 on top, but we do have that same meaning. When I write a -1 as a superscript, it means the inverse of the matrix on the left is the thing that shows up on the right. From the prologue, we saw some weird things with multiplication. We saw some nice things with multiplication, and we ended with 2 big questions. Which matrices have inverses and which don't, and how can you tell? How can you find the inverse of a matrix if there is one? For the rest of the video, we are going to give definite answers to both of these questions, specifically when we're dealing with 2 by 2 matrices. Later videos in this section will talk about the questions and answers for larger matrices. All right, for the 2 by 2 case, there's going to be a very useful concept that will form part of our answer. So let's back up for just a second and take a look at our matrix A. Let's suppose that it has entries which we label A, B, C, and D. The determinant of A is a number we get just by using this formula. This formula says we're going to multiply together entries and subtract, and we're going to do it in a crisscross pattern. A times D takes us down the main diagonal, minus B times C takes us on sort of this backwards diagonal. We're going to call whatever number that is, we're going to call that the determinant, and we're going to abbreviate it by det of our matrix. So for example, if we were to take the matrices we've seen on past slides, the determinant of the first matrix is A times D minus B times C. So -5 times -1 minus 2 times 3. Now that simplifies to just +5 minus +6. So we end up with -1 as the determinant of that matrix. -4, 6, -7 ends up having a determinant of +2. And 1, 2, 3, 6 ends up having a determinant of 0. Now you may start to suspect something based on this numerical evidence, but we'll jump right to the answer. For 2 by 2 matrices, we have this theorem. Suppose that A is a 2 by 2 matrix with entries A, B, C, and D. As long as AD minus BC is not equal to 0, then A definitely has an inverse. In fact, here's a formula for it. So remember, we just saw this. This is the determinant. If the determinant of A is not 0, then there's a formula for the inverse. And the formula says take 1 divided by AD minus BC. So 1 over this number, and we're guaranteed that this fraction is not undefined. And then we're going to rearrange the entries a bit. We're going to have A and D switch places from where they were. B and C will stay in their places, but they're going to change signs, both of them. So we've got 1 over the determinant times the matrix D minus B minus C, A. And as long as AD minus BC is not equal to 0, that will be the inverse of our matrix A. Now, if AD minus BC equals 0, then this formula doesn't make sense because you would be dividing by 0. It turns out that actually A has no inverse in that situation. So in other words, the determinant of A is equal to 0 exactly when A is a singular matrix. Let's try this formula out. So if we were to start with the matrix 1, 2, 3, 5, we've already seen an inverse for this, but let's just see what the formula gives us. First, we'll check the determinant. If is AD minus BC equal to 0, and 1 times 5 minus 2 times 3 gives us -1, the determinant is not 0, that means this formula should work. In fact, what we should do is take 1 over 1 times 5 minus 2 times 3 and multiply it by this matrix. Again, notice the pattern. 1 and 5 trade places. 2 and 3 stay where they are, but they get changes in their sign. So 5, 1, -2, -3. This fraction in the front is 1 over -1. So -1 is the value of that fraction, and when I multiply that scalar through this matrix, the entries turn into -5, +2, +3, -1. And that is what we saw earlier to be the matrix that is the inverse of 1, 2, 3, 5. So the formula works. If we were to take 1, 2, 3, 6, we saw before that this had a determinant of equal to 0. And so the formula, or the theorem rather, tells us that there will be no inverse for that matrix. Well, if we apply it one more time to this matrix, -4, 6, -7, 10, maybe you want to pause the video here and see if you can find the inverse out for yourself. We'll just wait a few seconds. Okay, and now if we do this, we're going to start with 1 over the determinant. So we'll have 1 over -40 minus -42. This fraction becomes 1 over +2. We're going to switch the entries around. 10 and -4 trade places. 6 and -7 end up changing signs. And then when we take 1/2 and multiply it through this matrix, that's where we get the 5, -3, 7/2, -2 we saw before. This theorem answers both of these questions. Which 2 by 2 matrices have inverses? It's exactly the ones where the determinant is not 0. Which ones do not have an inverse? It's the ones where the determinant is equal to 0. Now, if you wanted to find the inverse of a 2 by 2 matrix, you can. You just use the formula, 1 over the determinant times this rearranged version of the matrix. Now, if you wanted to see why this theorem is true, one direction is pretty simple, actually. Let's just take A, B, C, D, and let's take this formula for what we claim is the inverse, and let's multiply them together. Now, as you do this multiplication, you'll see that it works. You do end up with the identity matrix in the end. You'll also see why it's kind of important for AD minus BC to not equal 0. Try that out if you're interested. Now, on the other hand, we know that if AD minus BC equals 0, then we claim that there is no inverse. To do that, I'm going to suggest that you try to do something similar to what we did in the prologue video. What you might do is multiply by this unknown matrix W, X, Y, and Z. See if you can find out what this should be in order to create the identity matrix. If you write out the linear equations you get from this and start row reducing, you should see something similar to what we saw in the prologue. It will turn out that this system, the system that you get, does not have an inverse. All right, now there's another way of doing the second half of the proof. We'll get into that a little bit later, but that should get you started in thinking about why this theorem is true. Let's practice using that theorem in a few other situations. So taking a look at these 2 by 2 matrices, can we dig deeper into which ones do not have matrices, which ones do not have inverses rather? Is there anything you can tell just by looking at them? And we do know that taking the determinant and finding the determinant to be 0 is an easy way of deciding that these are all non-invertible matrices, or that these are all singular matrices. But as you stop worrying a little bit about the vocabulary and just take a look at the numbers, one thing you might notice that there seems to be patterns here. 1, 3 is almost 2, 6. If I just took that first column and times it by 2, I'd get the second column. Or if I took the first column and multiplied it by 1/2, I might turn 8, 1 into 4, 1/2. And so it certainly looks like in all of these, there seems to be a number that if you multiply the first column by, you should get the second column. The same thing is true if we look at the rows. If I multiply the row 1, 2 by 3, I'll get the row 3, 6. Multiplying 1, 1/2 by 8 gives me the row 8, 4. And so whether you look at rows or columns, it seems that one is equal to a multiple of the other. All right, now this is true, and this is exactly what we would expect if AD minus BC is equal to 0, because what you can do is move the BC to the other side there, and then if the denominator is not 0, you can divide both sides by AC, for instance, or by AB, and what you'll end up with are these two equations. What we're saying here is that the numbers in the second divided by the numbers in the first column are they have the same ratio. Or if you were to take the numbers in the second row, divide them by the numbers in the first row, you'll see that they have the same ratio. So one column is a multiple of the other, and one row is a multiple of the other. And for 2 by 2 matrices, these are two different ways of deciding whether a matrix is singular or non-invertible. You can recognize that there is no inverse if one column is clearly a multiple of the other. Okay, so applying that, can we decide which of these matrices, A and B, is singular, and which one is invertible? And then for the one that is invertible, can you find the inverse? Can you fill in this entry here so that the matrix below is guaranteed to be singular? And can you solve this matrix vector equation? Now, this is something that we know how to do from chapter 1, but maybe there's a new way of doing it using our ideas of inverses. Go ahead and think about that. Pause the video if you like. In a few seconds, we'll dive into the answers. Okay, for the first question, you're supposed to decide which of these matrices is invertible and which is singular. Hopefully you can take a quick look. Whether you compute the determinants or whether you just look at whether rows or columns are multiples of each other, you'll find that A is a singular matrix. It's definitely, it does not have an inverse. So that means B does, and to find the inverse, what we can do is take the determinant. 4 times 9 minus 6 times 2 is equal to 36 minus 12, which is 24. So the determinant is 24. Our inverse will be 1 over 24. And then remember, we'll want to swap the location of 9 and 4, change the sign on 6 and 2, and 124 times each of the entries in that matrix gives us a matrix with entries 3/8, minus 1/4, minus 1/12, 1/6. and so this is the inverse of B. For the second question, you were asked to fill in the entry so that the matrix below would be singular. And remember, singular means that the determinant should equal 0. And so if we called that unknown number x, then the determinant would be 10 times x minus 9 times 8. And if that were to be 0, we would need 10x to equal positive 72. And that means that x should be 72 tenths, or in other words, 7.2. And 7.2 is the number you can put in there to make the matrix non-invertible, or to make it singular. Finally, the matrix vector equation 2, 3, 5, 7 times the unknown vector x equals 5, 10. If you wanted to, you could definitely solve this by setting up an augmented matrix and just row reducing and figuring out what the entries of x should be. But let's take a look at this. We know how to solve something like 1/2 times x equals 9, where you just have a number times x equals a number. What would you do in that situation? Most of us would just multiply by 2, right? And we would get x equals 18. The reason why we would do that is because 2 and 1/2 are inverses of each other. So multiplying by 2 gets rid of the 1/2. And I just get x equals 2 times 9. 1/2 and 2 are inverses in the same way that 2, 3, 5, 7 and its inverse are. So if I were to compute the inverse of 2, 3, 5, 7, I can do that because the determinant is 14 minus 15. It's -1. So when I do the formula, I'll have 1 over -1 times this rearranged version, and that will give me -7, 3, 5, -2. If I take this inverse and I use it to get rid of the appearance of the 2, 3, 5, 7, I'll multiply that matrix on both sides. On the left-hand side, I'll just get the identity matrix. And the identity matrix times x, no matter what x is just going to give me back x. Now on the right-hand side, this times that, do that multiplication. So -5 times, -7 rather, times 5 plus 3 times 10 is -35 plus 30. That gives me -5 in the top row. And then 5 times 5, -2 times 10, gives me 5 on the bottom row. And so what I did is I cleared out the left-hand side by canceling out that matrix by multiplying by the inverse. The left-hand side just turned into x. The right-hand side just turns into -5, 5. And that tells me x is -5, 5. And if you were to do the matrix, the row reduction of an augmented matrix, this is the solution you should come up with as well. We're going to stop here for now. Here are our outcomes again. You want to be able to define what it means for a matrix to be invertible or singular or non-singular. You want to be able to define what the inverse is. And then for the situation where you're dealing with a 2x2 matrix, you want to remember that rule for inverses, that formula for inverses for 2x2 matrices. And then as we did in that last example, if you're able to find that inverse, be able to use it to solve a matrix vector equation like we've seen. All right, I will see you in the next video.